What's up, guys? Welcome back. I'm going to post this key for the Drone Projectile Lab as we're getting ready for Assessment 3 next week. So some pre-lab questions. Some of you forgot to do these, but real important stuff. So projectile lands at the same height it was launched from. The time up versus the time to come down is the same. So time up equals time down. Once the projectile leaves your hand, what forces affect it? So it's just gravity, the force of gravity. So we've talked about that a lot by now, but hopefully that's you're just thinking gravitational force on it right there. Time in the air determined by the vertical vector. Nothing horizontally affects the time that it's in the air for. Excuse me. So if I throw a ball upward at 20 meters per second, how long does it take to reach the top? So that's going to be 2 seconds, and that goes back to it's accelerating downward at 10 meters per second per second. So if I throw it upwards at 20, it's 1 second later it's going to be 10, 2 seconds later it's going to be 0 meters per second velocity. So it's going to be at the top. And then what formula do we use to determine the distance traveled while an object is accelerating? So for this we do distance equals 1/2 acceleration times time squared. That's kind of a remember it type equation. So you got to make sure that you're using that. We use that to figure out the distance that an object goes up or a distance downward. Let's say you went out and you threw these. So you've got certain whatever data here. That kind of doesn't make too much of a difference. But trial 1. I would expect, let's say this was an average of 5.5 meters, and the time in the air was something probably, let's say like 4.2 seconds. You were throwing it up high. So it didn't go very far, but it went up high. And then this one, let's say it had a close average time, we'll just say 4.5 seconds, but it would have gone a lot farther. So we'll say for this 19.6. So I'm just making up averages there. But what I expected was you threw the first one up high, so it didn't go very far, but it was still in the air for a decent amount of time. And then these vector ones, I'm going to take what I did in class and I'll copy and paste those in here. So hang on a second. All right, so we're right back here. So I'm just taking what I had in the notes yesterday and putting those in here with my comments on those. So make sure you pay attention to this and the things that I looked for, because you'll probably have to draw something like this on your assessment next week. So large vertical component. For the first one, these first two are opposite directions. One of the mistakes a lot of kids made was they added a vertical component at the top, which is not true. There's no vertical velocity at the top. That's different if I had said draw the acceleration vectors, because the acceleration vectors you would really do the same drawing as you do here for the force of gravity vectors. So if these were acceleration, it would be downward the whole time because of gravity, because of the force of gravity. So there's the force. And remember, a projectile in the physics sense of the word ignores air resistance. So we don't even have to think about that. And then the force that we threw it does not stay with it. That force that we put on it gets it in motion, and then its inertia keeps it moving horizontally. Let's see, trial 1 data. So what did we make up here? I used 5.5 meters, 4.2 seconds. All right, so I'm just going to put that in here, 5.5 meters and 4.2 seconds. So that's what your data would stem from, whatever you had for trial 1, your averages for those for the different measurements. So total time in the air, we would take to get to the time to the top, we would take total time divided by 2. So half of that time. So in this case, I'm doing 4.2 divided by 2, which equals 2.1 seconds. And then I use that to determine the initial vertical velocity. So some of you are still stuck on the vertical velocity being 0, which it's 0 if I drop it and it falls down. But if I'm throwing a ball up, its vertical velocity can't be 0 to start or it wouldn't go up. So to find this, initial vertical velocity, I take the time up times acceleration, which is 10. So to do that, I get 2.1 seconds times 10, so it equals 21 meters per second. And that's in the pre-lab questions. I said, if I throw a ball up at 20 meters per second, how long does it take to reach the top? Well, it takes 2 seconds. We're just thinking the same way, but with different quantities. So now I'm saying, okay, it took 2.1 seconds. How fast must it have been going? So to find that, you just multiply by 10. Now, knowing the time up, which equals the time to come down, determine the vertical height the ball went to. So here's where we're using that distance. Distance equals 1/2 a times t squared. And I've got to make sure that here I'm using just the time to go up. So that'll help me solve this correctly. So I do 1/2 of 10, which is the acceleration, times the time up, which was 2.1 seconds, and that's squared. So that's going to give me, that's going to be 5 times 2.1, which is 10.5. And I multiply that by 2.1, so what's that going to be? Is 21 plus, no, yeah, 21 times plus 1.05, so 22.15 meters. I better double check that, right? Oops, this doesn't want to work. How awkward is this, right? Let's see, 2.1, whoops, I cubed it. 2.1 squared times 5, 22.05. Good thing we double checked that, right? That would have been major. So then here we're determining the horizontal distance. We know the time in the air. We want to determine the initial velocity in the horizontal plane. So the horizontal velocity, v sub x. So in doing that, we are just going to take our horizontal distance and we divide that by the time. So it's just distance over time because it's not accelerating. And so our distance, we had measured 5.5 meters. And we divide that by 4.2 seconds. And that'll give us, oops, no, 2.3, that can't be right. 5.5 divided by 4.2, 1.3 meters per second. So we've got those. So then we think about, all right, what's true about the horizontal velocity? All that we want to know for this, constant. Doesn't change during the whole time. So now here's, to me, the good stuff is that we've got our initial vertical and horizontal, and we want to determine the actual velocity the ball left the hand with. So here I'm finding the resultant of these. And so I'm not going to draw the triangle in here, but we've got the horizontal component and the vertical component, and those make up the actual velocity, which is the hypotenuse of that triangle. So what I've got to do is it's square root of horizontal velocity squared and vertical velocity squared. So it's 21 squared plus, what was the vertical or horizontal, excuse me, 1.3 squared. And let's see. That equals 21.04. meters per second. So because this one's so big, this one's really small, and that doesn't really affect the hypotenuse too much, but that's the right way to do it. And then what was the speed of the ball when it landed? So a lot of you did a whole bunch of math to get this, but if I threw it at 21.04 meters per second, it's going to land at 21.04 meters per second. So very conceptual, those are just the same. When you think about the vectors at the beginning, they look like this. At the end, they would look like this. So the hypotenuse of those are the same. It's just moving in a different direction. Now here, if the thrower was taller or stood on top of an igloo or a building and threw it, how would this affect the range? So here, almost exaggerated in your head. If you threw this from like on top of Holt High School, you threw it the exact same way, the ball would go farther. It would increase the range because the ball is in the air longer. So now that it's in the air longer, it can travel horizontally more. So that's going to increase the range on that. And then here, if I doubled the mass of the ball, how would my calculations be affected? Well, they wouldn't be affected. So no effect. And we talked in class, but one thing, it would be harder to accelerate the ball to that initial velocity. So throwing it would be harder, but assuming you got it to the same velocity, it would have no effect on there. So I think that's everything. So hope this helps, and let me know if you have questions.